Good evening, everyone. Welcome to Steward Observatory. Welcome to the decade of the 20s. It's a new year and a new decade here, and we're very happy that you've come to join us this evening. Before I introduce tonight's speaker for the first Steward Public Evening of 2020, I wanted to show you our schedule. It's been changing around a lot. If you checked it last month, we were going to have a speaker from South Africa, and then he's now no longer coming, so that got canceled. So this is what's going on, okay? And we've had to move some dates. Next week, okay, the Large Synoptic Survey Telescope is now called the Vera Rubin Observatory, okay? So LSST becomes VRO. Now, the Dark Energy Science Committee for the Vera Rubin Observatory is meeting here next week in Tucson. And the people who have staged that meeting wanted to do a panel discussion, okay? So, and then they said, we'll do it on the Monday. I said, fine, you know that's Martin Luther King Day. Yeah, we'll do it on the Monday. Then they said, oh, it's Martin Luther King Day, let's do it on the Tuesday. Yeah, okay, so we moved it to next Tuesday. So next Tuesday, in this room, there will be those four astronomers from Rutgers, Duke, University of Toronto, and whatever SLAC stands for. They will be here together with many of these other scientists. They're going to talk about cosmology in crisis, the universe expanding quicker than it should. What are some of the issues that they want to address, the big science they want to address with the Vera Rubin telescope, formerly the Large Synoptic Survey Telescope, when it goes online later this decade. So, and notice it's going to start at 7, because they want to do a 90-minute presentation. They want to go from 7 to 8:30. So unlike our other talks, next Tuesday night, the panel discussion will begin at 7 o'clock in this room. Now, I just put this up because I forgot to last month. I'm also the president of Phi Beta Kappa here at the University of Arizona. And every year we have a visiting scholar. This year our visiting scholar is Professor Francis Su from Harvey Mudd College. He's a mathematician, and he has a public lecture. We're going to be inviting the students who get invited to join Phi Beta Kappa to come and learn about the organization, but you're also invited. It's going to happen Thursday night, January 30th. On Wednesday, you're going to get the abstract. Those of you on our mailing list, Kathy's going to send out all of these changes for January, and she's going to send you the abstract for the talk, Mathematics for Human Flourishing. So that's going to be a special mathematics talk on January 30th. On February 17th, Yancey Shirley will celebrate 50 years of radio astronomy here in southern Arizona. If you'll remember, Catherine Greer is the astronomer who got sick in November and couldn't give her talk. So she is going to give that talk on March the 2nd. March 9th is spring break here at the university, but there is another astronomy meeting having to do with the Dark Energy Spectroscopic Instrument at the big 4-meter telescope up at Kitt Peak. They haven't told me yet who their speaker is going to be. It'll probably be someone from out of town, but that'll be on the 9th. On the 16th of March, we're going to have our Spanish language lecture with our new Bach Fellow, Dr. Cristobal Petrovich. That'll be in Spanish. Then on March the 30th, one of our new postdocs, Dr. Vivian Miranda, she will be here to give a talk, and she hasn't given me the title yet, but I'll get it up there as soon as we can, and I'm still looking for a speaker for April 13th. So there's our tentative plan for today. I don't have to make the announcement about stamping assignments, because classes don't begin till Wednesday. And you know what? I don't know if the telescope's going to be open. I told our telescope operators, but I don't even know if they're back yet. So I'll let you know at the end of the talk if somebody showed up to open up the telescope. So it may or may not be open. All right. I could, but I want to go home and watch the rest of the football game. All right. So I am happy tonight to introduce our first public evening speaker for the decade of the 20s and for the year 2020, Dr. Thomas Beatty. Thomas originally hails from Connecticut. He received his bachelor's degree in astronomy from Harvard, and then he received his PhD in astronomy from the Ohio State University. He was then a Chu Fellow. His first postdoctoral fellowship was at Penn State University. And a year and a half ago, in fall of 2018, he arrived here from Penn State. So without further ado, I will introduce Dr. Thomas Beatty to talk about, once you've discovered another Earth, what comes next.
Can you guys hear me? All right. I was going to say, thank you for that introduction, Tom. It's always nice being introduced by another Tom because I feel like we're on the same wavelength on a lot of things. Right, so I'm going to talk to you tonight about exoplanet atmospheres. So what I do, my day job is I work on the James Webb Space Telescope. 2 out of the 4 instruments on James Webb are built here at Arizona. So I'm on the instrument team for one of them, an instrument called NIRCam. And I work on the NIRCam program to look at exoplanet atmospheres. We're going to get up, we're going to use the telescope to look at these atmospheres and see what these planets are made out of. And before I really get into the talk, it's going to go for me. Yeah. I wanted to just sort of make a brief philosophical point, which is that a lot of what we work on, and by we I mean people who work on extrasolar planets and people who are looking at their atmospheres, a lot of what we're working on these days are things that in many ways people have been wondering about for hundreds and even thousands of years. Astronomy is probably one of the oldest human sciences. We looked up at the night sky and just said, what's going on up there? And we're still doing that today. And one of the first questions you can imagine asking if you look up at the night sky and say, what's going on up there? Is there anywhere else like Earth in the night sky? And what we're working on today is finally getting at an answer to that question. And I'm going to talk to you a little bit about how we do that and then how we plan to do that in the future. So I'll begin just by reminding you about what I mean when I talk about extrasolar planets. So in the solar system, we have a bunch of planets. This is 9. Pluto snuck in there. 8 planets, depending upon how you want to do it. But all of our planets are orbiting the sun. When I talk about extrasolar planets, what I mean is that planets that are orbiting other stars that are within our galaxy, usually that are tens to hundreds of light years away. We know of extrasolar planets that are thousands of light years away, but those are generally so far away that we don't get a lot of really useful information about them. So these are relatively close by, galactically speaking, and they're planets that are orbiting other stars. Until 1995, these were the planets that we knew about. This is a very standard diagram. If you go to extrasolar planet conferences, you will get sick of seeing this diagram of orbital size and planetary radius. But these are the planets we knew about. These are the solar system planets. Today, we know a lot more planets that exist. And there are actually a couple of interesting features in this diagram. One is this gap right here. You can sort of see that gap is actually real right down there. What's happening there is those are small planets that are evaporating. So things that are very close to their stars, if they're that big, they keep onto the gas and they can hold on to it. If they're this small, they're like Earth. They don't have a large atmosphere. In the middle, the star is stripping away all the gas and blasting them into pieces. We also, when we were originally looking at this, we didn't expect to see planets in this sort of short orbit. We've determined that what's happening is these planets are migrating in. You can see there's sort of a gap right here, and there's planets on one side or the other. That's telling you that migration either happens and it works, or it doesn't happen and the planets stay where they were born. So you can learn a lot about this diagram, which is why you see it a lot at the conferences. But the short version is we now know of about 1,800 planets that are confirmed, I would say, in about 1,200 star systems. So in the last 25 years, we've gone from 8 or 9, take your pick, to about 1,800, 2,000. A lot of that has been done using the Kepler spacecraft, which you may have heard about. That was launched back in 2010 and 2 years ago, stopped operating. Kepler is effectively just a giant Schmidt camera that we put into space. If you ever get a chance to look at the CCD module, there's some engineering pictures. It is an amazing image to look at how they built the CCD module, because they built it for the field curvature, the Schmidt. It's actually a very elegant piece of machinery. But Kepler found about 300 planet candidates. And I'm using the word candidate there very deliberately, because what Kepler sees is it sees the planet passing in front of the star. I'm going to talk a little bit more about what that means, but that gives you a radius for the planet. It turns out there are a lot of things out there that have the radii that are about Jupiter radius. There are a lot of things that go bump in the night that look like planets but aren't actually planets. I spent about 4 years of my life in grad school doing what Kepler did, but doing it from the ground. And we probably looked at about 300 objects, and we got 10 planets out the other side, because we had a hit rate of about 90% of things that we looked at, and it turns out not to be planets, even though initially it did. So there are a lot of false positives that exist in these surveys. So I'm using candidate there because we think they're real. We've tried to vet them, but we haven't done that completely, and we're not exactly certain that these are actually planets. Okay, so I mentioned that Kepler does transits. Let's see if I can get this to run. Right, so the way the transit method works is that if the angle is right between you and the planetary system you're looking at, the planet will pass in front of the star from your perspective. Jupiter passing in front of the star, passing in front of the sun, would make the sun get dimmer by about 1%. And it takes about 12 hours for Jupiter to go in front of the sun if you were looking at us from another star. That 1% is something that is now easily measurable using even a modest-sized 12-inch, 8-inch telescope and a CCD. So we can measure Jupiter's passing in front of the sun. If the planet is smaller, if the planet is something like the size of Earth, that depth goes down a lot. It's an area ratio, so as the radius gets smaller, it goes as the square of the radius. So Earth is 1/10 about the size of Jupiter. So that means that instead of 1%, it's 1/100th of a percent is what we're looking at. That is much more difficult to measure. That's pretty much impossible to measure from the ground, and you can only do it from space. Interestingly enough, actually, I said that you can measure 1% dips with CCDs now. You actually could probably have done it with photographic plates even back into the 50s. If you knew where to look, you could have detected transiting hot Jupiters by the mid-50s. And it was actually, a couple people sort of suggested to just make the attempt, but the idea that something the size of Jupiter would exist on a 3-day orbit 5 stellar radii away from its host star was regarded as so insane that nobody thought it was even worth doing the attempt. So it's interesting to think that we could have actually found extrasolar planets 50 years ago if somebody had just gone out and tried to do it, and also gotten a little bit lucky. Right, and then the other thing, so transits give you a radius. It tells you the diameter of the planet. To get the masses of the planet, which is the other key part of this, is we use a technique called radial velocity, which is the planet and the stars, they go around each other, are not actually, the star is orbiting a little bit too. The star is orbiting around the center of mass of the two objects in the system. And so the star is moving it a little bit around in a circle with the planetary orbital period, and we can measure the spectrum from the star moves because of the Doppler shift. It moves one way and then the other because of the Doppler shifted light changing the frequency that we see. And we can measure that change in frequency. We can measure the velocity of the star as a function of time. And that tells us roughly that tells us the mass ratio of the star to planet is. And we can usually estimate what the star's mass is using theoretical models and expectations. The limit, the rough limit these days for stellar radial velocity is about 1 meter per second, which is about this fast. So this is about how fast we can measure stars moving, even out to hundreds of light years over the spans of tens or even 100 days. So we've gotten very good at measuring these small motions in the stars. And I mentioned that transits could have been done 50 years ago. The first precision radial velocity survey that could have detected a hot Jupiter was done in the mid-'80s by a pair of guys called Campbell and Walker, who were at the University of British Columbia. And I met Campbell at a conference a couple of years ago. And they had, it's a little bit technical, but they had to use radioactive, I think it was some sort of uranium gas as a part of their instrument setup to try and measure the wavelengths very precisely. And they had to heat it up because they needed it in gas form. And so one of them was in the telescope observing, and if this thing cracked the gas cell that contained this, they had about 30 seconds to get out of there before they were going to get irradiated. And so the other one would be observing, and the other one would be in a radiation suit with the hood down outside, just waiting for this cell to crack so he could pull the other guy out and save him. And so they did this for maybe 2 years. They looked at about 25 systems. They didn't see anything. Statistically, actually, they should have seen something. They got unlucky. They should have found something back in like 1985. And so we were at this conference at the drinks portion of the conference, and I was talking to Campbell, and I asked him, do you ever feel bad that you guys probably should have gotten a hit here? And he was like, yeah, I've thought about that a lot, but I'm going to be honest. We got those observations. Neither of us died. I think we came out ahead. Okay, so that's how we get diameters and masses for these planets. That gives us a density. It tells you a lot about what's going on with the planet. And one of the things that we look for when we look for these planets and try and find them is we're trying to look for things that are in the habitable zone. And by that I mean something that is the right distance from its star to be about the same temperature as Earth. And there's a lot of thought devoted to what does that actually mean, right? Like we think Earth has liquid water on it, so we want something to be at the same distance, but can we be a little bit closer in? Can we be a little bit farther out? What exactly is the width of the habitable zone? That's something that's still really very much up in the air, an ongoing piece of research. So I'm not really going to go into it other than to say that we have an idea that something about Earth's temperature is where we want to look around these stars. And for missions like Kepler, we have a lot of possible candidates. We have a lot of things that look like they're Earth radii that are at the right distance from their stars to have liquid water on them. The problem is for a lot of them, we don't have any masses. So the radial velocity method works best on relatively bright stars. A lot of the Kepler planets are around fainter stars where it's very difficult to measure radial velocity. Another problem is that I said that we can measure radial velocities to about 1 meter per second, about walking speed. The Earth, the velocity change on the sun that the Earth exerts is about 10 centimeters per second. So instead of walking speed, that's sort of maybe about this. That's something that is not currently, I don't want to say possible, it's extremely difficult. There are people who can do it, but it is an immense amount of effort. It's very difficult, and it's not clear that any of the detections are actually real at the moment. So we don't have we don't really have any masses for these things. So we have a problem, right? Because we see these things that we think are habitable. This is what we get. We get this planet going in front of the star. The star gets dimmer. We can measure the radius. We know the radius pretty well. But the problem is we want to figure out if this planet is actually a nice beach vacation like Earth with liquid water, or if it's going to melt anything that lands on it and is like Venus. Because Venus and Earth are very close in mass and radius, and Venus is very close to Earth's distance from the sun. If we were looking at the solar system from another star, we would say that the sun had 2 habitable planets. Because we have 2 roughly Earth-sized planets at roughly the right distances. The problem is just knowing, even if you knew the masses, right? Just knowing the mass and radius and the distance from the star isn't the final word, because you can have whatever the distance is between Earth and Venus. And so to figure that out, we need to look at these planetary atmospheres and see what's going on and see if it's a nice place or if it's actually filled with sulfuric acid and is going to melt us if we try and land. Another fun side story actually about that Venus picture is that's from one of the Soviet Venera landers. And as it was, I think this one, as it was coming down, The camera that was used to take that picture had a lens cap on it, right, to shield it as it went through re-entry. And so as the parachutes come off, the lens cap pops off. There's some spring-loaded thing. The lander lands, and then there also was a spring-loaded arm that was designed to fire out, scoop into the ground, and then it was going to retract and pull some of the soil back into the lander. And so they land, they start taking pictures, they fire the spring-loaded arm, and the arm went directly into the lens cap, which had landed about 6 inches away from the lander. They didn't have enough time to solve this because the Venera lander melted after about 2 hours on the surface. I think that it was in the 80s, maybe? Somebody said, when was that? All right, so the easiest way to solve this problem would be to actually take an image of the planet, right? You can look at the Earth. It looks like a pretty nice place to visit. And you can imagine that maybe we don't get that nice a picture. We get something that's sort of pixelated. But you could still tell from that it's a good vacation spot. The problem is that Earth is about 10 billion times fainter than the sun. And so the common analogy that people use when they're talking about this is that it's the equivalent of standing in New York City, trying to image a firefly that is in Los Angeles, and the firefly is about 5 feet away from a searchlight. And actually, as I was making this slide, I was sort of doing the math on some scratch paper. And actually, this analogy doesn't really work because the Firefly analogy, because that's actually a lot easier than what it would take to image the Earth around another star, probably by about a factor of 100. So it's an extremely difficult problem to try and do that. There are people who are working on it. There's a big mission that's currently proposed that's called LUVOIR that would probably launch in 2035, 2040. That could potentially do this, but it's putting a 16-meter mirror in space, and you have a star shade, and it would be a large effort. So we're getting close to the point where we can do this, but we can't do that yet. So the other way we do this, and the way I actually do it, is measure the atmosphere using more indirect methods. And there are two sort of general ways you can divide this up. First is you can look at the planet as it passes in front of the star. That's labeled on that diagram as primary eclipse. I'm probably going to say primary transit most of this talk. The other way to do it is to look as the planet goes behind the star into secondary eclipse. I'm going to talk about that in a second. When the planet goes in front of the star, what we see is, imagine Earth. Earth is a solid ball of rock, we'll say. And then on top of that, we have some thin atmosphere. So as Earth goes in front of the sun, and we were looking at it, the sunlight would come, it would hit the rock, and it would stop. It get absorbed by the sunlight. Other sunlight would pass through the atmosphere on the very edge of the Earth, sort of in a ring from our perspective at a distance. And we would be able to see, and we can see, that attenuated starlight that passes through the outer part of the atmosphere on these planets. And that's what this diagram is trying to show us. Here's starlight that's coming at us. It's a little bit attenuated. And that attenuation allows us to measure the components of the atmosphere. But the problem is there are a couple of failure modes here. One, if the planet doesn't really have an atmosphere or has a lot of gravity, you don't really get much of a signal. The atmosphere is too low down and you don't measure anything. Another problem is if it's cloudy. Right? Jupiter has a very strong cloud deck. If it's cloudy, you also don't measure anything because you just hit the clouds and you're done. That actually seems to be the common thing that we're seeing for a lot of these smaller planets, is most of the smaller planets that are closer to Earth appear to be cloudy. So this is looking at that starlight as a function of wavelength. If there was water in the atmosphere and there were no clouds, we'd expect to see it to go up right here. There's a very strong water feature at that wavelengths, and we'd see that in the transmission spectrum. What we see is something that's perfectly flat. We know from the mass and the radius that the planet has a density that's too low for it to be composed only of rock. It has to have gas, some sort of gas, hydrogen, envelope on it. So there has to be some sort of atmosphere. We're not seeing an object that has no atmosphere. But we do see something that is flat as far as we can measure it. So what that's telling us is that when we look at this thing that it's very cloudy, that's preventing us from seeing deeper into the atmosphere and actually figuring out what's in it. So another way to do this and sort of get around this problem is to look at a secondary eclipse and even look at something called a phase curve. So this is another diagram. This is the transit. This is the planet passing in front of the star. And then as it goes behind the star, you also get a dip. Because as the planet goes behind the star from our perspective, we're seeing the bright day side. It goes behind the star. It drops down because we've suddenly lost the bright day side as it goes behind the star. So you can look just at secondary eclipse and you can measure the day side light coming off the planet. You can also look in between. As the day side rotates into view, you can see the whole planet get brighter, and then it goes behind the star, and then it gets dimmer again. And that is actually a very exciting technique. That's called phase curve observations. This is the only way that we actually have any sort of global information about the climates on extrasolar planets, and it actually even gives us some information about what the weather. Let's see if this repeats. Okay, so this is the planet is rotating into view, and the whole spectrum gets higher because we're seeing the bright day side, and then it goes down. And this is, let's do that again. So right here there's a big water feature. We expect to see water in the atmosphere. And so you can see as it comes up, there's this sort of divot there. It divots down right where you see water. So that's telling us that water is present over a large portion of the day side atmosphere. If you actually look at that in a little bit more detail, the water sort of comes and goes a little bit. And so what that allows us to do is it allows us, by tracking that shift, is it allows us to map out what the cloud coverage on these planets actually is. So this is a different system, but it gives the same idea. And what we see is that it's very cloudy in the morning. The night side is completely covered in clouds. The mornings are sort of partially cloudy. The clouds are burning off. At noon, it's sort of halfway, and by the afternoon, the clouds have pretty much cleared off, and then they reform once things cool down at night. And that jives with what we're seeing with the transmission spectroscopy, because that's really the light that's getting to us from those stars is going around the edge of the planet, right sort of at dawn and dusk, which is exactly where we see most of these clouds. And in transmission spectroscopy, I was saying that prevents us from seeing into the atmosphere. By using these sorts of phase curves and emission measurements, we can try and get around that and measure where the clouds exist, what's in the atmosphere, and even start to try and figure out what the clouds are made out of, and really get down to what is going on in these planets' atmospheres. I will say, though, that so far we pretty much only have hot and big planets. Those are the easiest to measure. These sorts of observations are very difficult to do. So at the moment, we don't have anything that's like Earth. We have a lot of things that are like Jupiter and that are hotter, but we don't have anything that's exactly like Earth. But I'm going to talk a little bit about when we get to the point where we can measure something like Earth, what are we actually going to look for? So that's how we're going to do it. We're going to look at things through transmission spectroscopy. We're going to look at the phase curves. We're going to use these techniques that we're using for hot Jupiters on smaller planets once we have the ability to measure something at higher precision. Okay, so how would we actually tell if there's life on these other planets? The first question is, what do you actually look for? And I'll say that there's, I think we all recognize that Earth is one particular case of life in the universe. I think the expectation is that when we find life, it may not look too much like what we're used to here. But we're faced with a little bit of it's sort of like the story about the drunk guy looking for his keys around the streetlight. And he's just looking around the streetlight, and somebody says, well, where'd you drop them? And he says, over there. And he says, well, why aren't you looking over there? He says, well, I can't see anything over there. So when we think about life on other planets, we think about it through the lens of what life on Earth is like. And that's not because I think people aren't thinking about what other life would be like, but we know one system that works. And so if we have to choose something to look for initially, we're going to look for that one thing that we know works. So what would you look for on Earth? Well, the first thing is what's in the atmosphere. There are a lot of things in Earth's atmosphere that distinguish it from the other terrestrial planets in the solar system and even Venus. So one major thing is Earth has a lot of oxygen in its atmosphere. So oxygen, if there was no life on Earth, we have about 20% of our atmosphere is oxygen. If there was no life on Earth, we would have probably about 0.1% of oxygen. So that is a large, what's called a biomarker, the presence of oxygen in Earth's atmosphere. Some other things, water is important just because that's important to our own biology. You could also look for methane. Methane is produced by a lot of organisms on Earth. One problem with methane is you can also produce it abiotically. There are geologic processes that can produce methane in pretty significant quantities. So one reason why people like looking for oxygen when we talk about biomarkers and looking for life on other planets is because there's not a lot of geologic processes that produce 20% oxygen. And the game is figuring out what can be produced by biology and what can be produced by geology, and where do those two not overlap. And so far, oxygen seems to be our best bet, but there are a lot of other indicators that you would actually look for, right? If you just saw oxygen, that could mean a lot of things. Maybe you're just catching the planet at a bad time. But if you saw oxygen, you saw water, you saw a little bit of methane, that would be something of a smoking gun. Right, and the reason is because all these things are very reactive. Oxygen wants to come out and rust on everything it comes into contact with. And the only reason why it exists in our atmosphere is because the plants are making it. Future space missions like JWST, James Webb, will barely be able to see a lot of these biomarkers around Earth-like planets around the smallest stars. To really do this, we're going to need to wait for the next generation space missions that are being talked about now, and I mean literally like right now. The big decadal survey that astronomy does is occurring this year. There have been meetings starting last month and are occurring right now, deciding what exactly we're going to build. Another thing you could look at besides oxygen is you could look at the spectra coming off the planet, the color of light coming off the planet. The main thing that people think about with Earth is something called the red edge. So this is Earth in optical visual light, what we're normally used to. This is Earth in the infrared. And you can see that the land on Earth is much redder. And the reason for that is that plants reflect a lot of infrared light. This is actually how plants keep themselves cool, is that if you were looking at a plant in the infrared, you'd get this blinding reflection coming off of it, because they're trying to dump all this waste heat that they get from the sun back out. And so you can see, if you take a spectrum, if you look at the color of a plant, sort of going from the optical into the infrared, there's this huge jump where the plant is absorbing as much optical visual light as it can, right? It's trying to pull that in and run photosynthesis. And as soon as you get into the infrared, it says nope, and starts trying to reflect all that back out into the air and into space to try and keep itself from overheating. That would be if we could detect that on an extrasolar planet, that would be a very strong signal that there's vegetation on that planet. And not only vegetation, but Earth-like vegetation that uses something like chlorophyll to conduct photosynthesis. Another thing, another thing is that oceans and land actually reflect light differently as well. And you can't really see it there, so you'll probably just have to take my word for it. You get slightly different colors from oceans and land. And people have done this experiment where they've taken spacecraft elsewhere in the solar system and looked back at Earth and tried to say, okay, let's try and reconstruct what the continents on Earth look like. And you don't get a nice map, but you get this sort of, you don't get any latitude information, but you do get longitudinal information. And you can see that, you know, oops, did I just run out of batteries? I think I did. Anyway, you can see that Africa and Asia are pretty big. There's an ocean, and you have the Americas, right? And so one thing that would let you do... All right, thanks. See, this is why it's good to have another Tom supervising these things. So one, that would tell you that there's water and there's land on another planet. that is actually something that's, the fact that Earth has both water and land, I don't want to say it's a coincidence because we don't actually know why that's the case. And what I mean by that is that is a very fine balance, the fact that we have like 70% water, 30% land. If we had a little bit more water, we would just be an ocean world. If we had a little bit less water, we'd have no oceans at all. The fact that that balance seemed to exist on Earth is something that a lot of people actually puzzle over. And so seeing that on another planet seems to be also very indicative. And you'd also know that there's liquid water that exists on the surface from these sorts of measurements. I will say that one actual problem you'd run into with Earth is that if you didn't know the moon was there, you wouldn't actually recover the continents that we'd see. What you'd actually recover is that Earth has a 28-day rotation period. One side has all the land, one side has no land on it at all. If you didn't know the moon was there, because you can't see the moon from distance, and you just end up recovering the moon's orbital period. All right, so that's a little bit about life. You could also think about, could we look for evidence of technology on these other planets? And this has been going on for decades through the various SETI searches looking for radio or optical signals through lasers from other stars. But one thing is it can be somewhat difficult to know what you're seeing when you look at that. This is something actually that was taken at Ohio State. It's called the WOW signal. They were doing radio observations, and they suddenly got this very just strong, sharp pulse of radio energy that, if it was coming from the Earth, would look a lot actually like a ballistic missile search radar. But they only got it for a second, and they never saw it again, and it just sort of jumped off the charts. And nobody's actually been able to explain what caused this. But it can be hard to know what you're seeing, because you get something like the WOW signal, and maybe we were, an alien starship was sweeping us with its search radar, or maybe it was some astrophysical signal that we're just not familiar with. Right, so what about the planets themselves? And I'm saying that because over the last 10 years, we have gotten very good at measuring the atmospheric signals from planets. And as we think about biosignatures, we're going to get even better at measuring the atmospheric signatures from these planets. And that opens the door to SETI searches that don't just rely on active emissions, like active radio broadcasts from extraterrestrial life. It opens the door to directly looking for signs of technology on planetary surfaces using the techniques we use to measure planetary atmospheres. So one thing you could ask is, can we see industrial pollution? I've been talking a lot about atmospheric composition. Could we see industrial pollutants in the atmosphere of a planet like Earth or on another star? One problem is that industrial pollution usually stays pretty low. Right? This is why smog exists, is it settles down to the bottom of valleys. To see things, we really need it to be lofted up into the atmosphere. That's where it's most easily to be seen. But you can talk about, what are the major smog components on Earth? Nitrous oxide, methane, CFCs. The top two have a lot of possible natural sources. If you saw a lot of nitrous oxide, you saw a lot of methane. There are a lot of other things, even biology, that could be creating them. Biology would, of course, be super interesting in its own right, but it's not detection of aliens. CFCs have pretty much don't exist in the natural world. If we saw CFCs, that would be it'd be hard to say what that is other than some sort of industrial civilization on another planet. And they last for a long time, right? It's sort of the problem with CFCs, actually, but they last for up to 100,000 years in an atmosphere. So there'd be if a species was putting them out, they'd stay up in the atmosphere. There's really nothing else that would produce them that we can think of. So if we saw them, that would be a pretty neat. The problem is that Earth's spectra, the atmosphere around where CFCs exist, is very complicated. So there's a lot of other things that are up there that are absorbing starlight and sort of confusing us. So unless we had atmospheric concentrations that are about 10 times what exist on present-day Earth, we couldn't detect it even with sort of the next generation space telescopes around the closest planets. And by the time you're at 10 times the present-day Earth, it's not really a nice vacation spot. It's probably some sort of post-apocalyptic wasteland. So we could detect that. I don't know if that would probably be the most depressing resolution to the SETI search, actually. That we found them, it turns out they just destroyed themselves. But one other thing you could actually look for, and this is actually something that I'm working on right now, is could we detect city lights on the night sides of these planets? If you look at Earth at night, it's actually a very strong, Earth at night, most of Earth is pretty black. If you were just in space, you'd be able to see the city lights pretty easily. And most of the street lights that we use, sort of the sodium pressure lamps, actually have pretty narrow spectral lines, pretty concentrated emission right in the core. Is this gonna, yeah, right in the core of the sodium line. And so what you could do is you could look for this. And you couldn't do this with present-day facilities. You'd need to wait for these next-generation instruments. But these next-generation instruments are going to be looking at these planets. They're going to be trying to look at planets like Earth, if and when we find them, and try and measure their atmospheres extremely precisely to try and determine if there's oxygen, to try and determine what they're made out of, what's going on in the atmosphere. So you'd actually get city light observations for free. You wouldn't have to do any additional observations. And so what you'd look for is you'd have your observations to try and figure out what the atmosphere is made out of, and you'd get your oxygen and water, and it would look like a beautiful Earth-like atmosphere. And then on top of that, you'd get these strong sodium emission lines present from the night side city lights. There's nothing on Earth that can produce that sort of energetic sodium emission in our atmosphere. And for urban levels that are 10 to more than what we have on Earth, we'd actually be able to detect that around Alpha Centauri and a lot of the nearby stars like Tau Ceti, Epsilon Eridani, the sort of greatest hits from science fiction. So with the next generation observatories, this would actually be a way to try and directly detect the presence of urban civilizations on other planets. And I'm going to come back to this slide just as my end, my stopping point. And I'm going to end again with another little bit of a philosophical thought, which is I mentioned at the beginning that astronomy is one of the oldest sciences that we have and is one of the oldest ways that we have tried to understand where we fit in the universe. And for probably the last 2,000-3,000 years, people have been wondering, is there anywhere else like Earth out there? And if there is, are there other people like us on those planets? And we are this close to actually answering that question. Right? People here at Steward, you guys in the room, within the next 20 years, we will actually have an answer to that question that people have been wondering about for 3,000 years, which is something that is very exciting. And I think for us, I feel like we often get lost a little bit in the day-to-day of fighting with the computers and writing emails. But when you stop back and think about what we're trying to do with things like James Webb and with the next generation observatories and measuring what's going on with these planets, it's very exciting, and I'm happy to tell you about it tonight. So I will stop there and take questions. Thank you.
Okay, we have plenty of time for questions for Dr. Beatty. Question here.
Very interesting talk. You're a great speaker. Question, what's preventing us from moving faster, doing what you'd like to see happen? Is it the technology of the new instrumentation, or is it the money to create the new instrumentation, or is it the politics that manages all that, or all of that put together?
Yeah, so Well, yeah, I mean, the frustrating answer is it's a little bit of all three. So one of the ideas that people think about is when we're trying to take images of a planet like Earth, is the idea of with launching into space what's called a star shade, which would be a giant object that's probably tens of kilometers across that you'd put out in front of the telescope and that would block the light from the nearby star. And that would have to be 1,000 kilometers away from the telescope. You'd have to position it to within centimeters relative to your telescope that's also in space, which to me seems like an insane engineering challenge. And I once asked one of the people who was working on this, is this actually possible? And he said, yeah, if you spend enough money, anything's possible. So, and that's what I mean, that it's a very strong technological challenge. There are solutions that right now probably just cost a lot of money. And as a practical matter, NASA's budget has been $20 billion for the last, 2 decades-ish. Because anything higher than that, and Congress starts paying attention. So that's where we're at. Right, what I would like to see happen is for us to launch something called LUVOIR, which would be a 16-meter mirror into space. But there's a lot of technological hurdles that could be solved with money, but can be a tough sell.
If you do find evidence of extrasolar life, will it be announced right away, like a normal scientific discovery, or will the government want to keep it quiet? Like in the movies.
Yeah, right. Yeah, no. I guess I've never understood in the movie. I mean, in the movies, you have to have it because what else are you going to do? It's not clear to me. So, as I lay awake in the middle of the night and think about what I would do when I discover extraterrestrial life, besides writing my Nobel Prize acceptance speech, the actual difficulty would be if you got a detection and you were sure about it. The usual process once you get something like that is it can take a month or even more to actually write something up and get something that's publishable that really would stake your claim to it. And so in my mind, the actual challenge would be how do you survive that month without everybody else blabbing all over the world or you blabbing all over the world. I think if we found extraterrestrial life, the challenge would not be the government shutting us down. It would be somehow preventing every astronomer in the world who found out about this from yelling at the top of their lungs from the nearest mountaintop that this occurred.
When you talk about the habitable zone, I'm reminded of, the Goldilocks zone. I'm reminded of Star Trek using type M planets. What is the correct terminology that we should use for habitable zones?
It's a good question. The terminology doesn't, like a lot of things in the English language, it sort of evolves as it evolves. I've been at conferences where people have tried to create terminology. They tried to call transiting planets tranits, which lasted for about the duration of the talk, and then everybody forgot about it. So habitable zone you'll see usually in papers. Goldilocks zone is, my sense is that's a little bit more used by the astrobiology community and less the astronomy community. I would say most astronomers know what a Class M planet is because we're all Star Trek nerds at heart, but nobody actually uses that in the literature.
Just some clarification. So the transiting of the planet can give you the size of the planet, and the radial shift can give you the mass. How do you determine how far, or the orbit of the planet, where it's located in relation to the star?
Yeah, so that's so another thing you get from both the radial velocity and the transits is you get a orbital period as well.
Third law.
Yeah, so with Kepler's third law.
Transiting at the pole or transiting at the equator, couldn't it?
Yes, it does actually. That's that's a quantity called the impact parameter. So yeah, so the transit duration changes as a function of the latitude of the transit. but the orbital period doesn't. So the center of the transits are going to occur every orbital period. And if it's at a higher latitude, you'll get the sides of the transits will be much steeper because it takes longer to completely cross over entirely onto the star. So you can, when you fit for these things, you fit for the period and you fit for the latitude of the transit as well as part of the fitting process. Yes.
Yeah, you said you had a lot of false positives when you were identifying planets. What were the other objects that you saw?
So the way I used to describe this is it was sort of like doing like online dating with people. That there were weekends, right, where we would get something on like a Friday afternoon, and I was like, we had been working on this for years to try and find our first planet. And we'd get something that looked really likely, and they'd say, okay, we're going to look at it over the weekend, and we'll let you know Monday morning. And even though they weren't going to email me before Monday, I'd just sit there hitting refresh and thing. And right, you go into these things very hopeful, and then every time it ends up at some sort of, it's a lot of red flags, right? Usually what they were is eclipsing binaries. So we were looking for planets about the size of Jupiter. The smallest stars also have the same radius or diameter as Jupiter. So from a radius perspective, you can't tell them apart. They look exactly the same. So that was a pretty common failure mode. Sometimes we just have, the camera would see something that didn't actually exist. That was sort of the worst one. Sometimes you'd had something nearby that was sort of blended in, that was a lot deeper, and so when we actually looked at it, we'd see something that was 10 times the size of Jupiter and clearly couldn't be possible. But I think the ones that really burned my heart were the eclipsing binaries, because there were a lot that seemed very, like they were really going to be the one to settle down with, and they ended up being these small stars that probably are only loved by sentimental astronomers.
When Drake came up with his equation in the early 60s, he really didn't have any good numbers for the factors he put into it. It seems over the last 50-some years, we've been able to start getting those factors. If you were to take an estimate right now with what you know, what would you think the result of the Drake equation would be?
That's so that's something I think about. I forget all of the factors that go into it, but roughly, let's say there's 100 billion stars in the galaxy. Let's say there are a billion of them that are like the sun enough or sufficient for life. Our rough estimate is about a third of the stars like the sun have something that could potentially be habitable. So that gets us down to 300 million. But at that point, we lose it, right? So once you have a habitable planet, what determines if you turn into Venus? What determines if you turn into Earth? We don't know. I will say that, so one way to think about SETI, right, is we haven't seen anything in the last 50 years. That's actually a result. It's not the result we wanted. But there was a scenario where, Drake opens up the telescope, looks at Tau Ceti, and he finds broadcasts from, whoever. And it turns out there's a thriving interstellar civilization around us. That's not the case, at least not as far as we can see. So I think that the remaining factors in the Drake equation are probably pretty low. Right? This is also the Fermi paradox. If aliens exist, why haven't we seen them? And it's not actually a paradox, because the answer may just be aliens don't exist. That's actually an interesting thing. We think about it as a paradox because it's unacceptable intellectually for any of us to think that aliens don't exist elsewhere in the galaxy, but that's a completely reasonable solution. It could just be that we're a complete one-off. That, I think, tells us something very important about human nature that maybe we don't have time to go into. But I think that we're unfortunately reaching the point where the remaining factors in the Drake equation have to be pretty low.
Of course, it could also be the case that interstellar space travel is just not practical.
That's true.
Yeah.
Well, and that's why, so once we do the biomarkers, we'll get a pretty good handle, I think, on how many planets have life. And this is actually why I like the idea of doing SETI as sort of looking directly at the planets instead of relying on radio transmissions, because you could think about constraining everything in the Drake equation that way, right? Maybe we don't get a hit, we look at 10 planets, we don't get anything, but that gives you an upper limit, and you can actually start putting some real numbers on everything.
Like those factors for industrial civilizations.
Right,
and,
exactly.
whether life evolves or not.
Yeah.
Yes, any more questions? Oh, we have a few more.
So we're working very hard to make bigger and better observatories from near-Earth orbit. When are we going to consider going somewhere to look for things?
That's, I often think if we saw an Earth-like planet around Alpha Centauri that had biomarkers on it, what would you do then? The short answer is right now there's nowhere to go, which is sort of a problem, and it's very hard to get there. I think realistically, if we were even going to do something to Alpha Centauri, some sort of flyby mission, you'd need the next generation observatories to launch. That's probably 2040. You need to really be sure you're seeing something that probably gets you to 2045, 2050, and then you need to build it, and you need to go there. That's probably 2100 at the earliest. And that's assuming we actually see something worth going to. Like I said, I think a lot of astronomers are closet Star Trek nerds, or not so closeted. So I would love to have a warp drive and be able to actually go see these things, but I think doing it with telescopes is probably the best we can hope for the foreseeable future.
Question here?
Are either of you familiar with the rare Earth hypothesis?
The rare Earth hypothesis?
Yeah, it was written by a couple of, an astronomer and a biologist and I think a geologist wrote the book about 20 years ago now. And it's just that when you consider all the different possible coincidences that have occurred to make life here possible, that we have a Jupiter that acts as an asteroid deflector, right? And that, and a moon that keeps our seasons stable and so on, that it could very well be that we are a one-off because there were just so many coincidences that occurred to make life rare.
Yeah, I'll come at that from a slightly different angle, which is I go to conferences and there are sessions where people talk about sort of astrobiology and life on other planets and things, and they talk a lot about the Archean Earth and all these sorts of different things. And it's a very editorial comment. My personal sense is that if we find life on another planet, we have all these theories, right, about what determines whether or not life arises on planets. And when we actually find it, somebody's going to say, oh, no, it turns out that was what was important the whole time, right? We have lots of different possible things it can be. And it's very up in the air at the moment. So the rare Earth hypothesis is completely reasonable, given what we know. That could very well be the answer. It could also be that we put up a 16-meter mirror and a star shade, we start looking and we just get hit after hit after hit, and it turns out that it doesn't actually really matter that life finds a way anyways. At this point, I don't think we can say one way or the other.
Take a last question up here.
Okay.
Question would be, do you see anything in all these possibilities you're looking at an aurora borealis on any of these things showing some type of atmosphere?
Yeah, well, yeah, so we certainly see that on other planets in the solar system. We see aurora. People have actually, so people have tried to look for that on large Jupiter-like planets around other stars. Because that would give you a measurement of the planetary magnetic field, which is interesting for a variety of reasons. If we got to the point where we were really in detail looking at an Earth-like planet, I actually think looking for aurora and looking for auroral emission, because that's a very distinct spectral feature, would be a very good way of measuring a terrestrial planet's magnetic field. And the magnetic field on Earth is very important to retaining our atmosphere. So I think that's actually probably a pretty key component of what we look for.
All right. Unfortunately, the telescope isn't open tonight, so I guess none of our students got back in time. But I hope that some of you will be able to join our panel discussion next Tuesday, which is the 21st of January. Remember, it starts at 7 o'clock. It'll be in this room at 7 o'clock on the 21st. And let's thank Dr. Beatty one more time.